evening. For this programme, we're going to deal with gas giants and the formation of the solar system. Well, we know that our Earth is an ordinary planet, one of 8, and they're divided neatly into 2 groups. The small rocky planets, Mercury, Venus, Earth and Mars, then the asteroid belt, and then the 4 giants, Jupiter, Saturn, Uranus and Neptune, and the members of the Kuiper belt, including Pluto. Well, how did they get there? I'm joined now by 2 experts, Professor Richard Nelson of Queen Mary University, London, and Dr. Dave Rothery of the Open University. Welcome to the Sky at Night. May I come to you first, Richard? How were the gas giants formed?
Well, the gas giants formed basically within a rotating disk of gas and dust, which formed around the young sun. And there's a number of stages which you need to go through in order to form a gas giant. First of all, these small dust grains which are orbiting within the gas disk collide and stick together due to random motions in the disk forcing them to come together. As they stick together, they grow to become larger and larger planetary bodies. And in the outer parts of the solar system where the temperature is lower, you also have ices forming as well due to the condensation of water, methane and ammonia, and this increases the amount of solid material available to you. So you're able to build up large planetary cores, typically of masses around 10 or 15 Earth masses.
How far back in time are we going?
Oh, well, this process starts off at the very earliest stages of the solar system when the sun is forming and the gas disk is settling around it. This process of forming these planetary cores, if you like, takes around, well, maybe about 1 million years or so. Once you have a core in place of this required mass of 15 or 10 Earth masses, then it's able to attract the gas from the surrounding protoplanetary disk. And early on, that gas is settling on rather slowly, taking about 1 million years or so to get up to about 50 Earth masses. But once you get up to about 50 Earth masses, then the gas comes on very quickly and forms a disk around the planet, and that disk of gas then accretes onto the planet, allows it to grow into a gas giant like we see today in the solar system.
But there are various theories, are there not, David?
There are. Richard has told us currently the most popular view, and it's still most widely accepted, but I think it's fair to say there are still some problems with it. Some people will say that you can't grow these large cores at the distance of Jupiter and Saturn and beyond in time to scavenge all the gas that we see around these planets before the gas would have been dispersed by the strong early solar wind. So another model is based around not growing a core and then scavenging the gas, but based around gravitational instabilities in the disk of gas and dust within the solar nebula. And these instabilities, these dense knots, grow directly into giant planets.
Why did they occur in the first place?
It's very complicated, but you've got different rotation periods. The rotation period increases as you go outwards from the sun, and you can get spiral density waves forming within the solar nebula, just as you do within our galaxy. The spiral pattern is to do with, once you get some gravitational instability developed, the pattern propagates. So we get these dense clots in the nebula. And maybe one way to bring the core accretion model and the gravitational instability model together to allow things to happen sufficiently fast is to say you get a gravitational instability which gives you a dense ring at an appropriate distance in the solar nebula, and within that you can grow a core much more quickly than without this gravitational instability, and that may get round the problems of have we got time to do it all before we lose the material.
Where do you stand on this, Richard?
Well, I'm something of an agnostic, but perhaps veering towards the traditional model of core instability. And really I base that judgment on the observation that the giant planets in our solar system could have actually been much bigger. They could have accreted more gas if they were born in a very dense gaseous environment. Certainly if you look at Saturn, it's only about 1/3 of the mass of Jupiter. It could have grown to be much larger if there was a reservoir of gas available to it. If you look at Uranus and Neptune, then they are basically what we call ice giants.
Yes.
These are planets which are basically composed of rock and ice cores, surrounded perhaps by 2 Earth masses of gas only. And again, if they were born in a dense gaseous environment, they could have accreted more gas. So I think that's providing evidence that, at least in our solar system, planetary formation does take a long time. It's not unreasonable to assume that it comes to an end whilst the gas is being dispersed by this T-Tauri wind.
A T-Tauri wind, what exactly is that?
When stars are very young, they're particularly active. We can see it today. There's a particular variable star called T Tauri from which the whole phenomenon is named. And stars in their T Tauri stage have particularly strong stellar winds and particularly strong ultraviolet radiation, which acts to disperse the remaining gas around a young star. And when the T Tauri wind of the sun kicked in, it would have taken away the material which would otherwise have been accreted onto the outer giant planets. Uranus and Neptune are probably a lot less massive than they would have been because the T Tauri wind kicked in, drove the gas away, and there was less material available to accrete onto those planets.
Now, what about the rocky planets? I mean, we know the age of the Earth is about 4,500 million years, but how did the rocky planets form?
Well, whilst the giant planets are forming on the outside by the build-up of these cores, a similar process is going on in the inner solar system, except now you don't have the icy material around to help you. So you just have basically carbon and silicon grains which are sticking together to form these larger bodies. And basically what happens there is that these bodies can grow to become about the size of maybe the Moon or Mars. And after that time, there's a slowdown in the growth of the planets, and you have to wait for about 50 million years for the final stages to be complete.
What about the asteroid belt and the Kuiper belt?
Well, the asteroid belt is beyond Mars, and you probably would have grown a terrestrial planet, a Mars-like planet there, but the small planetesimals were unable to stick together. Jupiter was stirring them up. They're in slightly more eccentric orbits than they would otherwise be, and the collisions were sufficiently violent that when these small bodies bumped into one another, fragmentation was just as likely an outcome as accretion. So you didn't grow a planet there. The Kuiper belt, out beyond Neptune, is icy material which has never come together to grow into large bodies. The bodies are a long way apart. If you see a graphic of the Kuiper belt, you see little objects everywhere, but there's a lot of space in between. And this is just the icy debris, much of which was disturbed, perturbed as Uranus and Neptune migrated outwards. But most of the Kuiper belt is objects which are very primitive, very unevolved, and when we get a chance to look at them, we're going to learn a lot about conditions in the very early solar system.
Well, please don't go away. We're coming back shortly. Meanwhile, Jupiter had been high in the sky, and a few nights ago, a group of amateur observers joined Chris at my telescope to see whether they could have a good view of the giant planet.
When Jupiter's in the sky, it's absolutely unmistakable, the most brilliant thing around. At the minute, it's shining out in the evening sky among the stars of the constellation of Libra. Unfortunately, it's completely cloudy tonight, but it was clear last night, and you can get some incredible images with a telescope like Patrick's. So, what do we see?
Well, Chris, on this image of Jupiter, we can see both the equatorial belts, which are the most obvious things we can see through a telescope looking at Jupiter, and we can also see the Great Red Spot and oval BA, which is a very interesting object at the moment. It's formerly a white storm, which is coloured red, same as the Great Red Spot, and is moving very close to the Great Red Spot at the moment. It's a very exciting time for astronomers to observe this.
And Damian, there are many more features to look at.
Indeed, Chris. Jupiter is an incredibly dynamic world, and as we can see in the image, we have the two obvious equatorial belts, the beautiful blue festoons which are frequently seen coming off the edge into the equatorial area of Jupiter. But a particular feature of interest also, we have two white spots here which have been closing up for the last few weeks, and amateurs are now expecting that these features will merge shortly, so it will be quite dramatic to watch two large storms collide on the planet. Last year I was able to obtain many images of Jupiter and create some fascinating time-lapse movies of the clouds and storms and features moving on the planet. It's a very dynamic world, and animations really do bring it to life.
And that's a good example, Ian, of how things change on Jupiter from not just hour to hour, but across the course of weeks and months and even years.
Yes, indeed. I think Jupiter is a very exciting planet to observe. I've been observing it for many, many years, and it does change so much from day to day, month to month, year to year. And it's such a large disk in a telescope when you observe it. Amateurs can see details immediately on the face of Jupiter. And there is no other planet like it. I mean, Saturn looks beautiful and it's incredibly stunning, but Jupiter's the detail on Jupiter that changes that's so exciting, and I've drawn it for many, many years, and now I'm imaging it with CCD cameras, and you can imagine the power of the winds, etc., that have to generate these features. So it's really fascinating.
Jupiter's always brilliant in the sky, but we're having a hard time of it here in the UK this time round.
Yes, we are, Chris. At the moment it's very low in the sky, so we're looking through a lot of haze, looking through a lot of turbulence low in the atmosphere, which makes the whole image shimmer through the telescope eyepiece. So to capture an image of it is quite difficult from the UK at the moment. We've recently captured some images from abroad in Barbados. From that latitude, Jupiter was much higher in the sky, and from there we were able to get very steady images and produce a lot better data.
Well, it's Earth's atmosphere and clouds that have defeated us today. But when they're not in the way, the results are spectacular, and nothing more so than the Great Red Spot and its new companion, Oval BA.
Oh, thank you, Chris. Well, now, I'm joined by Dr. John Rogers, the Director of the Jupiter section of the British Astronomical Association. Welcome to the Sky at Night, John.
Good to see you.
Now, Jupiter is very prominent in the sky, and so can we have a brief rundown on Jupiter? A huge world, nearly 90,000 miles across.
Yes, well, everything we see on it is clouds. There are dark belts of dark clouds. The white zones are different sorts of clouds. And everything that we see is governed by the tremendous winds on the planet as well.
Indeed.
So not only is it the biggest planet in the solar system, it also has the biggest weather systems in the solar system.
How fast do the winds go?
Well, something up to 200 miles an hour. Even faster in some cases. The Great Red Spot has the fastest winds of all, reaching up to about 400 miles an hour.
Now, the Great Red Spot, the most prominent feature on Jupiter usually, when it can be seen. What exactly is it?
Well, it's an anticyclone. You know that on Earth we have cyclones and anticyclones, with low pressure systems and high pressure systems. On Jupiter there are similar kinds of weather systems, and the anticyclones are very large, very long-lived. The Great Red Spot has been around for at least a couple of centuries. So that is the biggest one, but there are others as well.
What is the back history of it?
Well, it's often said that the Great Red Spot has existed for more than 300 years, since the very first observations of spots on Jupiter, that it was discovered by Cassini in 1665. And he certainly did observe a spot that looked rather like the present Great Red Spot. It was small and dark and in the right place. But it was a bit smaller than the Great Red Spot is, and it was never seen after 1713.
And the red spot was observed again in the second part of the 19th century.
Yes, it was first detected in 1831 as a very broad, pale hollow, and that was how it appeared for the next 40 years. And I suspect actually that was the first observation of the present Great Red Spot, that it really was a very long and pale feature at that time. But in 1859 and again in 1870, it was observed as a dark elliptical ring, described as the Great Southern Ellipse.
Yes.
And it was just 3 years later, in 1873, using Lord Rosse's great reflector, that red colour was first seen in it. And I suspect that was actually the first time the Great Red Spot ever was red. And that colour developed over the rest of the 1870s until it was extremely vivid. In fact, the first photographs taken of Jupiter at the end of that decade show this huge dark red spot.
Well, I've been looking at Jupiter through various telescopes for 50 years and more now, and there's nothing as red as that in my experience.
There's nothing as big and as red as that, but this year there is something that is becoming red. The Great Red Spot has a companion, which was a white oval, but it's now becoming red, and that's caused a lot of interest.
Oval BA?
That's right.
There were some pictures here showing how it was formed.
Yes, originally there were these three ovals, just going around the planet as an array of equally spaced ovals, until one day they suddenly merged. Two of them merged first, while the planet was behind the sun, and then 2 years later the third oval merged with that one. And to everyone's surprise, this year it has begun to turn red.
Because one tends to forget how vast Jupiter is, and we are talking about features here which are tremendous compared with the Earth.
Yes, the Great Red Spot is about twice the diameter of the Earth. Oval BA is roughly the size of the Earth. So that's a single anticyclone, the size of our planet.
What will happen when the little red spot catches up with the big red spot?
Well, it'll probably glide past it. It does so every 2 years or so. But we're looking carefully to see if there's going to be any change to the colour. Because as features like that pass the Great Red Spot, there is often some instability in the cloud patterns. So since it's just adopted this new reddish colour, it'll be very interesting to see whether the reddish colour changes in any way. After that, I think we might see a new generation of similar white ovals appearing in the same latitude, but I can't say when. It may take many years for them to appear.
Well, one part of the magic of Jupiter, one never knows what's going to happen next. John, thank you very much.
Thank you, Patrick.
Further out, there are two worlds that are more aptly described as ice giants, Uranus and Neptune. So let's join Chris in the garden.
Both of the icy giants, Uranus and Neptune, are visible for the next few months from the UK. So, Pete, how do we find them?
Well, both objects are quite challenging at the moment because their altitude is quite low from the UK. Capricornus is a triangular constellation. The triangle is pointing down towards the horizon. But if you can find the stars on the left hand, the eastern side of the triangle, we have Delta, then Gamma, and then onto Iota, the third one in from that edge. And then if we go up from Iota to a faint star which is 18 Aquarii, find the midpoint between those two stars and move slightly to the east, and that's where Neptune is. Now over the next few months, Neptune is going to move across from that position above Iota. So if you can find Iota and then move up slightly from there, you should be able to find Neptune.
And it'll be visible in binoculars. Now Uranus, of course, is just about a naked eye object.
It is, but you have to have very good skies to see that. It's in the constellation of Aquarius, and I always have trouble with Aquarius because it's a very large, sprawling constellation, quite difficult to find your way around. But if you can then find Lambda Aquarii, and Lambda is the key to finding Uranus at the moment. To the east of Lambda is the star Phi Aquarii. During July, Uranus is midway between those two stars, and over the next few months, Uranus will move gradually westward and skirt just below the star Lambda Aquarii. So that's a good key to finding it.
So now we come to the question of what they look like, and I think the first thing to say is that they're clearly not just stars.
That's right. They're a long way off, these planets, so they are going to show us a very small disk, but it is a very noticeable disk. And the other aspect is you do notice the colour. Now Uranus has a disk, it's about 3 arc seconds, 3.6 arc seconds or so, and a small telescope will show you that pale greenish disk. Neptune is smaller, it's about 2 arc seconds across, and that's a bluey disk as well, and you do need a telescope to see, or binoculars to see Neptune.
But still, there's quite something, isn't there, to be looking up and seeing a distant world.
Absolutely, and I think that's really the appeal to seeing Uranus and Neptune. You just have the feel that you are seeing something which is there in our solar system, and it's a wonderful, wonderful thing.
So Uranus and Neptune are there, but of course much fainter than Jupiter and Saturn. Let's come now back to our story. 50 million years after the planet started being formed, we had a solar system, but not quite the solar system we have today.
No, that's right. In fact, current theory suggests that the solar system back then may have been in a more compact form, with the giant planets in particular closer together than they're observed today. So perhaps we can demonstrate what current theory suggests may have happened.
Yes.
So first of all, just let's recap what the architecture was back then of the outer planets. We would have had Jupiter, Saturn, and perhaps we would have had Neptune and then Uranus, because current theory suggests that there's a 50-50 probability that they may have swapped sides from the way they're currently observed. So we also have, outside of Uranus in this case, the Kuiper belt consisting of a disk of icy planetesimals. These are the leftovers of the planetary formation process, which form a disk beyond the orbits of the ice giants. If we consider now interactions between the ice giants and planetesimals, what happens is that over a timescale of around 600 million years after the beginning of the formation of the planets, the Kuiper belt bodies, these icy planetesimals, get perturbed onto orbits which cause them to scatter off the outer ice giant into the next ice giant. And then the gravitational field of the second ice giant scatters it into Saturn, and then Saturn scatters it into Jupiter. And Jupiter, being the most massive body in the solar system, throws it out of the solar system altogether or into the Oort cloud.
One thing worries me, the total mass of these planetesimals can't have been very great. How can that affect an ice giant?
Well, let's think about an individual planetesimal to start off with, and then think about what the whole sea of planetesimals would do later on. An individual planetesimal, when it scatters inwards off the outer ice giant, would cause the outer ice giant to move out ever so slightly. And when the outer ice giant sends that planetesimal into the second ice giant, it would then scatter it inwards and it would move out a little bit like this.
But the mass of the planetesimal is so small, how can that have any effect at all?
It's only moving it a very, very small amount, but when we consider the whole sea of planetesimals, we'll see that the total mass of that planetesimal sea, that planetesimal disk, was about 35 Earth masses. Now that is enough to start to move the planets around substantially. So basically you start off with a few planetesimals moving the ice giants out by scattering the planetesimals inwards, and then what we have is that Saturn moves out a little bit as it scatters the planetesimal inwards to Jupiter. Jupiter moves inwards, and then at a certain point in time what we have is a very specific configuration between Jupiter and Saturn. It's called a 2-to-1 mean motion resonance, and that arises when Jupiter goes round the Sun twice for every time that Saturn goes round exactly once. And this is dynamically important because this configuration can excite the eccentricities of the two inner planets there. And when Jupiter and Saturn become more eccentric, they also force Uranus and Neptune to become more eccentric, and then the system enters a chaotic phase of evolution where the two ice giants can scatter inwards and undergo a close encounter with Saturn and be scattered outwards into this planetesimal disk. And when they go into this planetesimal disk, they're then able to scatter this 35 Earth masses of stuff into the inner parts of the solar system, and as they do that they migrate out to their currently observed locations at 30 AU and 20 AU respectively.
So we have Uranus and Neptune migrating outwards. What other effects would that have?
Well, there's interesting geological evidence, Patrick, that the inner solar system was actually subject to a very heavy bombardment of comets and asteroids.
The so-called Great Bombardment.
Great, or the Late Heavy Bombardment, that's right.
If you look at the lunar highlands, the pale areas on the moon, they're saturated with craters. You could not fit more craters on there if you tried. You'd have to destroy an old crater to make room for a new one. That's the evidence of the late heavy bombardment. We don't know how long it lasted, but we know it tailed off at 3.9 billion years ago, and that's been dated from samples brought back from the moon. Now we can see ancient surfaces on the southern highlands of Mars or large parts of Mercury, but they've not been dated. But we think the whole inner solar system would have been subject to this bombardment. Yeah, you can't just hit the moon. You'd be hitting the Earth at the same time. But if you want to know about the Earth's early history, you have to look at the moon, because the Earth's been resurfaced many times.
Yeah, an interesting sideline in this, of course, is that the earliest evidence of life on Earth, of course, is also dated to be about 3.9 billion years ago. So that ties in rather nicely with the end, perhaps, of the late heavy bombardment. So there may be some relation.
And, of course, the satellites of the giant planets, they're also crater-pitted. At least most of them are.
Absolutely, but of course this is probably cratering from the last stages of the planetesimal accretion phase, when we're cleaning up the debris in the vicinity of the planets. Though of course some of them may have been subject to bombardment from these cometary bodies, these planetesimals coming from the Kuiper belt. But typically the regular satellites are rather close in, and the planetesimals typically wouldn't have smashed into those as much.
What about the so-called irregular satellites? Most of them are small, probably captured bodies.
Indeed, that's true. So these are satellites that could be on quite eccentric orbits, quite inclined orbits, and may be orbiting in either a prograde sense or in a retrograde sense. Probably the best example that we have in the solar system of an irregular satellite, certainly the most interesting, is Triton.
Because Triton's quite big.
It is indeed the largest irregular satellite in the solar system, 40% bigger than Pluto. Probably originated from the Kuiper belt during this period of outward migration of the ice giant and gas giant planets. So we have some recent ideas which have come forward about how Triton may have actually been captured around Neptune. And what it involves is basically binary Kuiper belt objects coming close to Neptune. And this is interesting because recent observations suggest that perhaps 10% of the Kuiper belt objects are not single Kuiper belt objects, but are binaries, that is, two Kuiper belt objects orbiting about each other. So let us perhaps try to demonstrate, using some very high technology props, precisely how this process happens. So let's take this balloon as being Neptune, which is orbiting in this direction around the Sun. Patrick, you can play the role of the Sun if you don't mind. You've got your nice yellow balloon to hand.
Here we are.
And then we have these two Kuiper belt objects which are orbiting around each other, coming past Neptune. One of them is captured into a retrograde orbit around Neptune, and the other one is flying off into interplanetary space. And basically the idea here is that you have to remove some energy from one of the bodies so that it gets captured around Neptune, and the other body takes that excess energy away with it when it travels off into interplanetary space.
If this body came in on its own, it would not get captured because it would have just too much momentum. It would carry on going.
Yes, it would.
You need the double object to do it. And many of these irregular satellites that are in retrograde orbits are quite small objects. And if they were orbiting a larger companion, it's a small one that tends to get captured. Triton is a special case. It's a very large body, bigger than Pluto. And for that to be captured, maybe Triton was part of a double system, and the body that escaped was even bigger than Triton.
That's right, indeed. So there could be some rather large bodies orbiting out there in the Kuiper Belt, which is yet to be found. Something rather like UB313 or Sedna or something like that even.
A good case of a binary Kuiper Belt object is, of course, Pluto.
Indeed, Pluto and Charon form a double Kuiper Belt object, but interestingly enough, Patrick, there have been two new objects found orbiting around Pluto. So
Nix and Hydra.
Nix and Hydra, so it's now a quadruple system rather than a binary system. So it's very interesting to find out in the future how many other Kuiper Belt objects also are triple systems, quadruple systems, maybe quintuple systems.
Yes, but Nix and Hydra are both very small.
They are indeed, only a few tens of kilometres in size, so perhaps not very interesting, forming a picture maybe of what the smaller end of the distribution of Kuiper Belt objects might have been like.
Well, what about this strange axial tilt of Uranus?
The old story about Uranus's tilt was it was hit by some kind of giant impact which knocks the whole thing over.
Doesn't sound very likely to me.
It's fairly implausible and very difficult to carry the satellite system with you without... They'd all bump into one another and get destroyed. A more acceptable view is that during the period of intense gravitational interaction between Uranus and Neptune, or Uranus and Saturn, the planetary tilt gradually migrated until it was tipped over to its present 98 degrees, and that taking a few 100,000 or a few million years, there'd be plenty of time to take the satellites with the planet, because tidal forces would keep the satellite orbits in the equatorial plane, following the equatorial bulge. So the tilt of Uranus would have happened at the same time as Uranus and Neptune were migrating.
Uranus has now been known for 1.5 Uranian years, but Neptune's more dynamic, is it not?
It is indeed, and observations of Neptune show that its upper atmosphere perhaps is more active than that of Uranus, and possibly one reason for this is that there is an internal heat source within all of the giant planets, apart from perhaps Uranus. And this heat source is basically related to the fact that the planets are gravitationally contracting still, releasing energy, and there is some separation of the different chemical constituents occurring within the interiors of these planets, which also leads to a release of heat. And essentially it's this heat upwelling through the planet up into the atmosphere which is able to drive a dynamic atmosphere and may be responsible for some of the clouds and some of the spot-like features which have been observed on Neptune.
Richard, David, thank you very much. Don't forget, it's newsletter time. If you want your newsletter, then send your stamped addressed envelope to the following address: The Sky at Night, Newsletter, BBC Birmingham, B1 1RF. Next month, we're going to come back to the inner part of the solar system because we're getting ready for a new onslaught upon Mars. Until then, good night.
The challenges, wit and wisdom of one family living with manic depression. A rare insight from Storyville, sunny intervals and showers tomorrow at 10. An 18th century literary fraud next tonight on BBC4. The Great Ossian Hoax.